Swayam Prabha. Digital India. Educated India.
Hello and welcome to this lecture of the course elements of mechanical vibrations. In the past lecture we have discussed how a typical vibratory system can be modeled as a 2 degree of freedom system where possible, and we have formulated the governing equations of motion, found out the natural frequencies and got introduced to the mode shape concept. In those discussions we did not include the external force in the equations of motion, and therefore, it will be interesting for us to understand how the response of such 2 degree of freedom systems to external harmonic excitation force is obtained and what are the response features associated with it. But before we do that, I would take couple of interesting examples on this 2 degree of freedom system, and then we will start with the forced vibration response. Okay, let us take an example now on the same car body having rear and front suspension and the CG located as shown here at distance L1 and L2. So the example is like this. The data related to the vehicle is already given here, as you notice, and in addition what it says is that the expansion joints on a concrete highway are 14 meter apart, as you see here. Of course, this is not a scale drawing. These joints act as a source of impulsive excitation at equal intervals to the car as it cruises, so as it moves with certain velocity, these expansion joints, which are typically there in to take care of the expansion with the changing temperature, they provide impulsive excitation to the wheel at regular intervals, isn't it? So, if we assume a constant cruising speed, you will have such kind of impulses every time the car wheels cross over them. Okay. Assuming constant cruising speed, and you need to find out the discomforting speeds assuming level road. So, that means there are no undulations on the road profile here, it is assumed to be absolutely flat, so that the excitation to the wheels only happen at the expansion joint. So, as the wheel crosses or moves past these expansion joints, there is a slight small impulsive excitation that take place. For the sake of simplicity, we are simply assuming that the wheelbase is reasonably small as compared to the distance. Okay, this obviously, if you add up this L1 and L2, it's going to be close to about 3 meters. So less than 10 times the distance between the expansion joints. So we can assume that these, in reality, the impulses will happen like this. Okay, but we can assume that there is a regular excitation to the car coming from the base, and we are supposed to find what is the discomforting speed of the car for the passenger. Okay. Now, discomforting speed will happen when the vehicle's natural frequency on suspension is matching with the excitation frequency from the base, isn't it? We have seen in the case of a single degree of freedom system also that if you are, the road profile waviness has a frequency of based on the speed, that frequency of excitation from the base matches with the natural frequency of the vehicle, it will have a larger amplitudes of vibration. Okay. So, when we are saying discomforting speed, it means that either of the two natural frequencies, we have found out that for a car body like this, there could be a pure bounce mode, there could be pure pitch mode, and when I say pure means the pitch mode and bounce mode are decoupled, and then if they are not decoupled, then you may have a coupled pitch and bounce mode, and then there will be two natural frequencies. Okay, and so if this excitation frequency, okay, which will be based on the cruising speed, so there will be some period for a given cruising speed which is constant, there will be a period for the repetition of these impulses to the wheel. Now if this period, if you translate it to an excitation frequency which is going to be 2 pi over this time period, if that matches with the either of the two natural frequencies, we may expect that the car body will oscillate or vibrate with larger amplitude than otherwise. Okay, and larger amplitudes means it may be discomforting for the passenger. So with these background and the question or a problem that we have, let us figure out what are those cruising speeds which could be discomforting for the passenger. Okay, what do you do now? The data is given. Now you already know what are the expressions for the natural frequency. If you recollect, px and p theta, these are the two frequencies, and in addition there are frequencies which are coupled, pitch and bounce. Okay, so this is bounce, this is pitch, representing these 2 degrees of freedom. So px theta 1 square and px theta 2 square, depending upon whether you choose negative or a positive sign here, you will get the two natural frequencies. Plus, if you want to know what is if the system has pure pitch mode or a pure bounce mode natural frequency, what is the way to find this out? By the way, this expression would be k1 plus k2, okay, upon m, and this could be k1 L1 square plus k2 L2 square over m rg square, where rg is the radius of gyration. So this is pure pitch mode natural frequency, and this is pure bounce mode natural frequency. How do I find whether the system has coupled pitch bounce mode or pure bounce pure pitch? Of course, this is a more generic expression, so without knowing that, if you appropriately substitute the values, you will get the two natural frequencies anyways. But I think we discussed this. When is the decoupling happens? When k2 L2 is equal to k1 L1, right? That is the condition that if these two values are equal, there will be decoupling and there will be pure pitch and pure bounce. Now these A, B, C, these parameters in this expression, I think they were discussed last. So these expressions, A is k1 plus k2 over m, B was defined as k2 L2 minus k1 L1 upon m, and then C was defined k1 L1 square plus k2 L2 square over m. So what are these values? These values are already given. So k1 is given, k2 is given, L1 is given, L2 is given, radius of gyration rg is given, and the mass of the car is also given. So you have everything that is required to find the two natural frequencies, all right, and we find that out. So if you substitute these values, of course you can show that this 27 times 1.34 is not going to be equal to 32.5 times 1.7. Okay, you can check this, it is definitely a larger value than this one. So this condition is not satisfied. So you basically have a coupled system here. That means whenever the car body moves up and down, there will be associated pitch motion. Okay, and so obviously if had they been decoupled, this is frequency equation would turn out two different frequencies, and they will be pure bounce and pure pitch natural frequencies. However, we are clear that they are coupled actually, and the two natural frequencies px theta 1, if you take negative sign from here, would be evaluated as 6.1 radians per second, or in cycles per second it turns out to be 0.96. If you substitute all the values with a positive sign here, you get the higher of the two natural frequencies, and that one will be 7.3 radians per second, or 1.16 hertz. Okay, and how do I find the two discomforting speeds now? Assuming that both the wheels will be almost getting impulses simultaneously, the repetition period is going to be dependent on the gap between these two, okay, and the speed with which this is going to cruise. Okay, and we have seen that. So the frequency of excitation would be how much? This will be V divided by the gap between the expansion joints, that is 14 meters, times 2 into pi. That's going to be radians per second, because the time period is going to be 14 divided by V. Okay, so the time for the vehicle to travel from this joint to this joint to get the next excitation, that time is going to be this 14 divided by the speed, and 1 over that multiplied by 2 pi is going to be the frequency in radians per second. Okay, so you have this omega, and we know that for a resonance condition px theta 1 should be same as this. Okay, or the other frequency or other speed will be px theta 1, px theta 2 can also match with this omega. So actually omega is something which I can replace in terms of 2 pi v over 14, and therefore the critical speed of cruising can be estimated. So from the first critical speed of the vehicle will be 14 px theta 1 over 2 pi, and the second critical speed is going to be 14 px theta 2 over 2 pi. There will be two speeds. Okay. All right, we shall discuss about few more things related to this example. So these are the speeds where the amplitudes are expected to be quite large, and human body is more sensitive at lower frequencies, and these frequencies are indeed quite low, and they will cause giddiness and discomfort. Okay, anyway, so let's look at other things in the sense we look at the dynamics little more in detail, right? So the rest of the example may not be so relevant to the problem posed, but we will take this opportunity to look at when they vibrate in that particular frequency, in which shape or mode or way it will vibrate. So x over theta is equal to b upon p squared minus a was the expression that we derived last time, and that actually is the mode shape. Okay, and so depending upon which value of p you use, the mode shape for that particular natural frequency gets defined. Okay, so if we substitute in this expression in this expression the value of P as Px theta 1, then we get the mode shape of the mass of this particular system when it vibrates naturally at that particular frequency. So, the first mode shape is defined by this ratio x over theta equal to minus 26.9. That is the value that you will get if you substitute all the values which you know A and B are known, and P is replaced by Px theta 1. This is the first mode shape. Now, you would wonder what this mode shape is going to look like. Now, I think we have seen that in earlier slides that the motion of the vehicle will be both pitch and bounce. So, x and theta will define those kind of motions. And similarly, in this expression, if you substitute for Px theta 2, you would get the next mode shape, and that is called and that is basically the second mode shape. Okay, and that is given as 0.75. Let's look at what these numbers mean in terms of the way this body vibrates, the car body vibrates. So, what we are going to look at is how do I find or how do I decide the shape of its movement in its free body or a free vibration. So, let us take the first mode shape here, x over theta is equal to minus 26.9. What do I make out of this number or a value? What I do is I assume that because there is degrees of freedom x and theta are defined at the CG, isn't it? So, what I say that suppose if I move this body, this CG with a displacement maybe 10 centimeter, just to have an idea about what this motion would look like. So, if I, because this is a mode shape, so it's a relative displacements, right? You are quite aware of that, we have discussed it many times. So, 0.1 could be millimeter, centimeter and so on, right? So, if I say 0.1 unit, what would be theta correspondingly, right? So, if I displace this vertically in the positive direction, because we have assumed x to be positive in the vertical direction, and theta was assumed positive clockwise, and so if x is given 0.1 unit of displacement, but let us assume that for the sake of clarity maybe 0.1 meters is the motion I give, what is going to be theta? Theta will have to behave, you know, given by this relationship, because this relationship should be always honored, or it should conform to this relative displacement to vibrate at its first natural frequency Px theta 1. So, if x displaces, if the body displaces by x equal to 0.1 meter, okay, then I can find out what would be the corresponding pitch, right? And that would be how much? 0.1, or maybe I should go step here. It is going to be 0.1, that is capital, sorry, yeah, capital X, okay, divided by minus 26.9, whatever that value turns out. Of course, that is going to be in radians, so I can, you know, I can convert that into degrees, because we are quite at ease understanding how much is the degree of rotation. So, it is quite straightforward for you to you know, find out that this theta would turn out to be 0.2 degrees. Okay. What does that mean? That if I move it by 0.1 unit, the pitch is going to be 0.2 degrees, but it is more correctly, this has to be minus 0.2 degrees if x is you know, pushed upward by plus 0.1, because this ratio is minus 26.9. Now, which actually means that um, you have to rotate um, the body in the counterclockwise sense. Okay, so if I move it vertically up, uh, the motion will be in the opposite direction like that. Okay, and then this body has to pitch like this, and this angle with horizontal is going to be 0.2 degrees. Okay, if you increase the displacement, let's say to 0.2 meters, you will have the same angle. But what we should be now trying to figure out is the position where this line, which represents the orientation of the body, where would it meet this mean position line, horizontal one. So this is the location where this line is going to intersect the normal mean equilibrium position line. Now this point can be obtained easily because that point is going to be given by let's say tan of 0.2 is going to be capital X over ln, I will call this. Okay, now what is capital X? We have displaced it by 0.1 unit, and I want to find out this distance ln. So this is 0.2 degrees, and that is my ln. Now that ln is this position, and you remember we have discussed in when we were discussing about the mode shape that there will be positions where there will be no displacement. The car body will have zero displacement at that point. So this is a node position where the entire body will have an oscillating motion about that particular point. So when it actually generates this kind of a bounce and coupled bounce and pitch mode, the position of the node can be obtained using this expression. You can figure this out, that it turns out to be 26.9. Now look at this distance. This distance was close to 3 meters, and 26.9 is the position of the node, right? So it means that the car is going to have very little oscillation or very little pitch when the bouncing is happening. So this first coupled pitch bounce mode is going to have predominant bounce motion and a very little pitch motion. Okay, and let us figure out what happens for the second mode. If you use this particular natural frequency in your expression of x over theta, it has given you 0.75. Now again, for this particular case, if I use the amplitude equal to 0.1 meter, what is the relative theta when x is so much? So it is always relative. This value will change if you change the value of x. Okay, so their ratio will be always maintained constant. Okay, now if you use this in the same expression as this, because here also in the second mode the body is going to not only bounce but it is also going to pitch. Now if that happens for 0.1 meter motion vertically up, theta is going to be 7.6 degrees. Okay, and if you calculate the position of the node, it's going to be 0.75. Now make a note here that this body which we have considered had the suspensions. Okay, the suspension, refer to the previous data which we have given. The CG is located here. This distance I think was 1.34 or so, and this one is I think 1.7 or so. Okay, now the node position from the CG is 0.75, which means that this is going to be the point about which the body is going to oscillate. So when it moves or when it pitches, this is how it is going to pitch. the angle turned will be significantly large as compared to the bounce. Okay, whereas in this case its pitch angle was almost zero, right? So it, when it moved up by 0.1 meter distance, the angle turn was very little, 0.2 is almost negligible, whereas here it moves by 7.6 degrees. That 7.6 degrees very close to G position or CG position, which is 0.75, is going to be making the oscillations more predominantly pitching. Okay, so first mode here is predominantly bounce, very little pitch, and in this case it is predominantly pitch with very little bounce. But theoretically both of them are coupled, the pitch motion and bounce motion both are coupled. So even when it is vibrating in the first mode or in the second mode, now both motions will simultaneously take place. Now this 0.2 degrees obviously appears too small, but is it not expected? Why it is expected? Because your CG, if you look at this 1.34 or 3, yeah, and 1.7 means it's almost close to the center between the two wheels, in the center of the wheelbase, and that is the reason why this angle is turning out to be very, very small. You try and shift this CG either this way or that way and make these two L1 and L2 reasonably different from each other, you will notice that this angle will change to a higher value. Okay, and then the coupled pitch bounce will be literally coupled pitch bounce, in which both bounce and pitch will be observed significantly. I mean, there will be a reasonable contribution from both the modes, but it suffices to say here that one of the two modes, px theta and px theta 1 and px theta 2, in one of these modes it is quite possible that either bounce will be predominant or the pitch will be predominant. Okay, and it all depends upon then the amount of coupling between the two motions, which is defined by B, which is basically K2L2 minus K1L1. The difference, if it is larger, you will have larger coupling and so on. So is this clear to you? How the discomforting speeds were obtained? They were actually directly coming from the two natural frequencies, so that when the periodic excitations are given to the wheelbase, depending upon what is the time period of repetition, one of these two modes will excite. And please make a note that even if the excitation is coming from the ground, because pitch is coupled to bounce and bounce is coupled to pitch, both these two motions will take place. Okay, having seen this, let me go back to this example which we discussed when we discussed the single degree of freedom system. You remember this? What did we do in the earlier case when we discussed this as a single degree of freedom model? We said that let us assume that this hoisting drum or a winch mass is negligible, okay, compared to the mass being lifted here. With that assumption, the stiffness of the beam, which I can call right here as K1, was directly connected in series to the stiffness of the rope, which is K2 here, and the load being lifted was the only mass in the system. And then we converted this into an equivalent spring mass system, and then we evaluated the natural frequencies, and we said that's the way we model it and find the dynamic characteristic. Now what if this m1 is not very small or negligible compared to the mass m2? what happens? Now we obviously have discussed this in the initial discussion of this multi-degree of freedom system, that if such is the case that m1 is not something which is very small compared to m2, we might as well include that in the model. And then what happens? Your model now turns out to be 2 mass or a 2 degree of freedom system like this. So this is the mass of the drum, right? And then this is the mass of the load being lifted, this is the stiffness of the beam, and this is the stiffness of the rope. And now you can get a more accurate estimate. Okay. Now what I have done here, that had we stuck to the single degree of freedom model and assumed mass m1 to be negligible, then there would be a natural frequency assuming only mass of the load. Okay, we neglect mass m1, so that is the natural frequency assuming single degree of freedom model. Whereas this model will give you two natural frequencies, let us say p1 and p2. That is what we found. Those the expression for such 2 degree of freedom system has already been derived, and we have the expressions of p1 and p2. So now what we have done is we have plotted these natural frequencies for different ratios of this drum mass and the mass of the load being lifted. Okay, for the sake of convenience, I am keeping the mass of the load to be constant 100 kg. Okay, the load mass is, let us say, 100 kg, and I start increasing the mass of the drum from, let us say, 5 kgs onwards. Okay, just to know in what way the characteristic change as we keep on increasing the mass of the drum, higher and higher till it reaches the mass of the load being lifted. Okay, so what you see here is, on the x axis I am plotting the mass of the drum or a winch till the value of that drum mass reaches 100 kg, same as the mass being lifted, that is 100 kg. Okay, let us first look at this point. I will be having two natural frequencies with the assumption of 2 degree of freedom system, right? When I use the data that the mass of the winch is 5 kgs and the mass of the load is 100 kgs, that means the load being lifted is 20 times larger than the mass of the drum, right? Huge difference in the two masses, 20 times. Now if this is the case, the first of the two natural frequencies will be close to 70 radians per second, and the other one will be about 625 or 630 radians per second. So you can see that there is almost like how much, almost 7-8 times, yeah, more than that, right? So almost 8 to 9 times larger frequency, the second one. Okay, in addition, I am plotting, of course, the natural frequency when it is single degree of freedom, assumed like single degree of freedom. So we neglect the mass of the winch, and obviously that line is going to be just one single value. So I am just plotting it for the sake of comparison here. Now as we keep on increasing the mass of the drum, the lower of the two natural frequencies slightly drop. So it changes from 70 to 60, 62 or so. So hardly maybe 10% drop in the value of the natural frequency as the mass of the drum keeps on increasing. You bring the mass sizable in its value compared to the mass of the load. Are you able to understand what is happening? We are changing the mass that we neglected, making it sizable compared to the other mass. Okay, when it happens, the second natural frequency keeps reducing, as you can see, and the gap between the two natural frequencies starts reducing. Okay. So what is the takeaway from this? I mean, what are we inferring is that if there is a large gap or a large difference in the two mass values, at least the lower of the two natural frequencies has absolutely no difference when you compare that value of the first natural frequency with the frequency that you obtain by assuming a single degree of freedom model. Do you agree with that? Right. So by neglecting this mass, the natural frequency that you get, that is omega n, is very close to p1. This is almost equal to the frequency that you obtain by assuming single degree of freedom model. The problem is only with p2. This p2 is of course a value which is going to be far away from the natural frequency, but then it actually helps. I will tell you how and why. Of course, as you keep increasing the drum mass, the gap between these two will reduce, but at the same time, please make a note that even when they are comparable, your first natural frequency is within 10% from your single degree of freedom model natural frequency. Okay. Okay, now what is the inference? What do you make out of it? You remember the Campbell diagram? You have a natural frequency and you have excitation line, then there is a intersection here, that's the resonance. Now you have a case here, let's say when the mass of the drum is very small, your first natural frequency is somewhere here, the second natural frequency is far off. Okay. Now even if your mass is sizable, right, maybe 33, 1/3 of the mass, you still are far off, maybe 4 times, 3 times to 4 times away in the second natural frequency, right? Now it all depends as to what is your excitation frequency vis-a-vis these two natural frequencies, right? In this particular case, as your rotational speed of the motor increases, of the drum increases, your excitation line is going to be like this. It's never going to touch or come anyway closer to your second natural frequency, right? So your prediction based on a simplistic model is going to give you reasonable estimate of both natural frequency, the relevant natural frequency, and also of your response as well. Because if you remain closer within this range of the first natural frequency, the contribution from the second mode to your response is going to be negligible. It will not affect your response. Okay. So when you do the modeling, now we are coming to our first step of the vibration analysis. When you do the modeling, the simplification that you make is also dependent on what is your operation, right? What are your operating conditions? What are your excitation frequencies? If the higher frequencies are far off, then there is no point in complicating your model, making it more complex, more time consuming to get the response, and you are not going to gain anything in terms of accuracy, right? Anything in the sense substantial change, right? Here you can see that it's quite obvious that there is hardly any difference if you had considered a single degree of freedom. So even if the mass keeps on becoming comparable, as long as your excitation frequencies are within this range, you really don't have to worry about the second natural frequency. Okay. And this graph basically tells you what is the difference between these two natural frequencies, um, and where the consideration of the second mass makes is more relevant. So now if suppose your second natural frequency is here and your operating speed is going to be here, then obviously there will be two critical speeds to cross, and then the second natural frequency estimation is essential, which means that you have to take the second mass and increase your degrees of freedom from 1 to 2. Now let us look at the forced vibration response. These are all natural frequencies, mode shape. I hope now things are very clear, crystal clear in terms of the mode shape, what they are actually. And let's now look at a practical system like a raft mounted compressor, which is basically going to have reciprocating uh, mechanism here. Let's say a reciprocating compressor, which is going to generate excitation to this compressor bed. Okay, so this is an entire compressor system, maybe driven by an electric motor, uh, and in ships typically what happens is that these equipment are not directly connected or mounted on the foundation, connected uh, to the hull. They put them on a bed called as the raft. Okay, so these are raft mounted equipment or machines, and the the equipment is isolated, as you notice here, from the raft. So there is one pair of isolators here, and then the raft itself is isolated from the hull or from the base. And so obviously if you look at this physical system, simplified model will be again 2 degree of freedom, 2 mass system. Okay, it's a simplistic model, obviously, even if it is involving 2 masses. In that we are considering only 1 degree of freedom per mass. That means the compressor is simply moving up and down, whereas in reality it may have some kind of a pitching mode as well. But for the sake of some of the important response features and characteristic, let us stick to only 1 degree of freedom per mass. And so this is the compressor mass, which is having a degree of freedom x1, and raft is m2, it has a degree of freedom x2, and that's how we model this practical system. What is the difference here now? That the compressor, being a rotating machinery, moving, it will excite the compressor structure with a dynamic force. So we are now including the forcing function in this 2 degree of freedom model. Okay, obviously this f of t is not going to be harmonic one for a reciprocating kind of a system. We know that there will be primary and secondary unbalanced forces which are going to have frequencies, uh, let's say omega and 2 omega. Omega is the rotational speed. So you may have f of t actually defined as f1 cos omega t, where omega is the rotational speed of the crank, and then f2 cos 2 omega t. Okay, the way we discussed in the single degree of freedom system, this now turns out to be a periodic excitation case. But we all know how to take care of the periodic excitation by individually estimating the response by one harmonic function, and then individually finding it corresponding to the second harmonic component, and then you simply add them up, assuming the linearity in the system. Okay, so let's focus on a harmonic excitation force. Now for the sake of again some illustration, I am including this spring, although in reality in that particular physical system that we considered, there is no spring from the top, but there is a reason why we are doing it for this particular small discussion. So this system is the one which we discussed in a introductory lecture of 2 degree of freedom system, right? We had k1, k2 and k3, and now this compressor is subjected to a harmonic excitation f cos omega t. Let us look at how does the compressor bed and the raft uh, will respond to this excitation f cos omega t, right? So this is the compressor and this is the raft. How will the response look like for the compressor, and how will the response look like for the raft? I hope you would agree that in our case, you would like x2 to be as small as possible. Now, why is that so? Because what is this? This is the hull of the ship, right? If you have a larger x of the raft, you will correspondingly have larger force going into the hull, right? That larger force, which is k3 into x2, is going to excite the hull structure, and the hull, if it vibrates, it is going to generate waves in the surrounding fluid, the water, right? The larger the amplitude here, now stronger is the intensity of the wave which is going to travel out, and easier it will be for the enemy to pick up the signal. Okay, so the design should be such that this entire system will have as little x2 as possible, so that the force transmitted to the base would be minimized and would be less, so that from the stealth point of view, your design is appropriate and better. Anyway, so that's another part. Let's focus on how do I get now the response x1 and x2 both as functions of time. How do you do that? We all know very simple and standard method is to get the free body diagram for both the masses. We have done this already for a 2 degree of freedom system. The only difference now will be an addition of this f cos omega t force. Rest of the things are as discussed earlier. So I will not go into the details of it, which you can follow easily. Just refer back to the initial discussions we had. Now, when you include this excitation force, the only thing changes is the term on the right hand side of the equation of mass m1, and so as you notice, f cos omega t appears on the right hand side as an excitation force. Raft is not subjected to any force, external force, and so that will have zero excitation force on the right side. The second equation is going to be like this. The first one is the only equation that has external excitation f cos omega t. Is that clear? How do you solve? Getting governing equations from the free body diagram and applying Newton's law is our step number 2. What is step number 3? Is to solve them. Now, all vibrations problems are solved by assuming a solution. What kind of a solution would be appropriate to assume here? So you assume the solution, what? x1t, what would you assume? x2t, what would you assume? We have discussed this in the case of a free vibration. We assumed it to be what? x1 cos pt. Did we assume? In the free vibration case of 2 degree of freedom system, we tried to find a harmonic solution, okay, a principal motion of the two masses, normal mode solution, where we assume that both masses will vibrate with the same frequency. So we said that they may have different amplitudes, but they should have the same oscillation frequency. Both the masses will move with the same frequency. With that, we obtained what? Mode shapes, natural frequencies. Here it is externally excited system. It's not a naturally vibrating system. It's not a free vibration case. So what is going to be x1t and x2t? In here also, the two masses will have can have different amplitudes. Okay, what will be the frequency with which they will vibrate? We all know for linear systems, they will respond at the same frequency. They will respond and they will vibrate, they will oscillate with the same frequency as that of the excitation, right? So external forcing function f cos omega t has a period of repetition and corresponding frequency as omega. So it is quite natural for a linear system that the mass will also vibrate with the same frequency and period of repetition. So cos omega t is the expected assumed solution. Here also it is going to be cos omega t. Now why is there no phase? There is no damping. Okay, if you assume the solution to be cos omega t, right, either it will be minus cos omega t, right, with of course amplitude square if you want to consider the acceleration term. So either displacement or acceleration, right. So the cos remains cos. Okay, the damping is going to introduce sine term or j omega term if you assume the solution to be capital X1 e to the power j omega t as the solution. Okay, so that is the reason the absence of damping allows us not to include the phase in this particular case. So x1 and x2 are the two assumed solution, and if you substitute now x1 and x2 into these equations, the intermediate simple mathematical manipulations I am skipping here for the sake of time, and you can easily show that when you substitute these assumed solution into these equations and solve, you would get the expression for capital X1 by separating the terms of X1. You will get this expression. Okay, don't worry about what all are there. Obviously you are observing that they are all functions of the system parameters k1, k2, k3, m1, m2 and f, as well as you can expect, because it is going to be dependent on the magnitude of the force, and of course the excitation frequency will obviously appear. Okay, what else? If you similarly do it for the second expression, you would get the expression for capital X2. Now since all these parameters are completely known, they are either system parameters k and m, and of course the force value and the frequency value, all of them are known. You give a given excitation to find the response. So if that all the things are known, you can find out the capital X1. What is capital X1? It is the amplitude of the response. So if this response is obtained, this is going to be capital X1. This is the amplitude, but the actual dynamic response, time dependent response, will be by substituting X1 its value, and the response is completely defined as cos omega t. Okay, so obviously the response would be like this, cos omega t, and amplitude will be X1. So at any instant of time you can calculate what is X1 t. Similarly X2 will give you the amplitude of the second mass by how much is going to be the amplitude of the second mass. It's given by this. Do you observe something interesting here? When will the compressor vibration becomes infinite? Very large. Can we say when the denominator is equal to 0? Isn't it? When the denominator, this expression is 0, amplitude will reach theoretically infinite value. Okay, huge amplitude. And if you notice, these two denominators are just identical. These are identical, and in fact if you solve this denominator equal to 0, you actually get the frequency expression, and you may compare now this expression what we solved for a simple a 2 degree of freedom free vibration case. This frequency equation is exactly same as the one which we obtained by assuming harmonic solution for both masses, and this was just the same expression. So it actually means that this equation will give you two values of the frequency, in this case the forcing frequency, where amplitudes will reach infinite value. And from the single degree of freedom system case, you already know what are that called resonances. Okay, when the value of omega 1 is equal to the natural frequency, you will have resonance. Now you have two natural frequencies, so you can get a second of the two frequencies from this frequency equation, which will be corresponding to the second natural frequency, and that basically is the resonance in the 2 degree of freedom system when it is subjected to harmonic excitation force. So when if I call this as the denominator, this entire expression in the denominator, if I set it to 0 and simplify and solve, I will get this frequency equation. Solving this quadratic in omega square gives me two resonance frequencies. Okay, so omega 1 and omega 2, and you would find that these two frequencies are identical to the first and second natural frequencies. Okay, all right. Now what we do is we take a simple case, the way we did it for the free vibration also, for figuring out what are the mode shapes and natural frequencies, right? We assume that this frequency, this stiffness K1 and K3 are equal to K, and this stiffness is equal to 2K, and the two masses are identical. I mean, this is done for understanding the response behavior. So there is no reason why these particular values are chosen. It is, you can choose any values, you will get similar response feature, but it becomes easier for us to discuss that. So we use these, and then if you substitute in the previous expressions of x1 and x2 that we derived in the or saw in the previous slide, you substitute k1 and k2 and k3, you get this expression. Okay, by simplifying for the values of k1, k2, k3, m1 and m2. So you get the denominator given by this, and the numerators of x1 and x2 are obviously two different values. You will realize what we are trying to do and why we are doing this. Simplifying it is only to get some discussion going. Now you remember that for a dynamic magnifier we normalize the response amplitude x with what? Static deflection or zero frequency deflection, just to get a non-dimensional response plot. Here also what we do is we normalize x1 and x2 by dividing it by f by k, and I can get f by k from the right hand side. And if I do that, the expression, this particular right side expression for both cases turns out to be these. So I take f and k from this denominator and then pull them below this x1 to get this ratio, which is now dimensionless response of the first mass, that is the compressor. This is the dimensionless response of the raft. Okay, and on the right hand side you have this expression wherein I have assumed r to be omega by what? Now I have used k over m. Okay, I need some reference frequency for normalizing it, right? I can take any frequency as such, but what I have done is, you remember that for this particular assumption, what was our first natural frequency of this system? When this was k, this was 2k, and this was k, this was m, and this was also m. The first natural frequency omega n1 or p1 was square root of k over m, because in that particular fundamental mode this spring was ineffective and both the masses were moving in the same direction with the same amplitude, so that this spring is ineffective, and it also turned out, and we discussed that this is almost like acting like an independent single degree of freedom, which will have natural frequency square root of k by m. Okay, so in a way this is the first natural frequency of the two natural frequencies of this system. So I am basically, instead of using omega n, I am using p1 as the first natural frequency for non-dimensionalizing or making a relative frequency or force frequency ratio is equal to omega by square root of k over m. So this r is the frequency ratio, and if I make sure that the frequency ratio is given by this, I will get this expression in terms of r. So this right hand side expression you can easily convert to this value. So the intermediate steps are all now excluded, just to focus on the response feature. So this is what I get as a dimensionless response of mass m1 and of mass m2 in terms of the frequency ratio. You remember, for the single degree of freedom system, x over xst, which is f over k, was for undamped case was given by 1 over 1 minus r square. You remember? Sorry, it is not square root, 1 upon 1 minus r square. Had it been a damped case, it would be 1 over square root of 1 minus r square whole square plus 2 zeta r whole square. Now in this case, zeta being 0, you get 1 upon 1 minus r square. Okay, this is for single degree of freedom system. The similar expression for 2 degree of freedom system is now going to be this. You expect it to have more terms and little more complex, right? Remember, the denominators are identical, which means that at certain value of r, both x1 and x2 will have large amplitudes. Okay, so for a multi degree of freedom system, when it vibrates naturally, so when it executes a free vibration in one of the natural frequency, all the masses move with the same frequency. Similarly, when they are at resonance, multi degree of freedom system, when they are at resonance, all the masses, okay, or all the mass elements of that multi degree of freedom system will also have large amplitudes. Their amplitudes will be large. Relative to the other frequencies, they will reach their maximum value. Of course, in some cases, depending upon the mode shape, some amplitudes will be 0, some of the masses will simply not move. We have seen the node position, but the resonance applies to every mass element in that multi degree of freedom system. Okay. Okay, moving on, let's now plot this x1 by f by k as a function of the frequency ratio. Okay, this r is called as the forced frequency ratio. Okay, because we have taken this r to be omega over square root of k over m, which is basically the first natural frequency. Now, in fact, as I told you that the denominator actually gives you the frequency equation, no? R square minus 1 into R square minus 5. If I equate it to 0, I should get the two frequencies, natural frequencies from this. You remember that I got, or you got R equal to 1. Now, this is the first resonance frequency in this case. The second resonance frequency is going to be square root of 5. Now, we have already seen that R is what? R is omega over square root of k over m. So if I write this R1 as omega 1 resonance frequency 1 equal to what? 1 times square root of k over m, and this omega 2, because R2 is going to be again omega m omega 2. So this R1 is going to be omega resonance 1 upon square root of k over m, and R2 is going to be omega resonance 2 upon square root of k over m. So this is going to be square root of 5 k by m. You can recall and flip your slides, and you can see that these are the two natural frequencies we got when k1 was equal to k3 equal to k, k2 was 2k, and m1 equal to m2 equal to m. These were the exact frequencies that we got in the earlier case, and by solving this denominator equal to 0, we are getting the two resonance frequencies. We are purposely not calling them as natural frequencies because this is the case of a forced vibration. Okay, so those are the resonance frequencies, and they are the frequencies where natural frequency will equal the excitation frequency. What do you expect now? You expect two resonances because there are two resonant frequencies, right? So if I plot this x1, versus or x1 by f by k, that is basically making it dimensionless. If this is plotted as a function of the frequency ratio, I will get this response. Now it is important for you to recall that we got this kind of a graph, right? Of course, this started with non-zero value like this, right? Whereas we are getting something slightly different here, right? And you recall that this x over xst was taken in mod sign. So we plotted the absolute value. We did not, because after resonance, actually if you look at x over xst for undamped case, 1 over 1 minus r square. So when r increases beyond 1, the whole ratio will turn out to be negative, right? But we plotted this an absolute value because we are interested in amplitude, not so much interested in what is the phase or in whether it is positive or negative, right? The amplitude is more important than the phase mostly. So here, because we sketched the variation of the amplitude of this dynamic magnifier with frequency ratio, it was shown almost always we show the resonance like that. Here we are not doing that way. We are plotting them with their signs as well. There is a reason for that. So I am plotting this as a function of frequency ratio, how the response of the compressor is going to look like. So as we expect, it starts with non-zero value. Why? Because when r is equal to 0, this is going to be 3 by 5 when r is equal to 0, isn't it? So this starts from 3 by 5 when r is equal to 0, and then as the speed increases or frequency increases, it shoots up, and then here you will have resonance, large amplitude at r equal to 1. We expect that. Why? Because our natural frequency, first natural frequency is square root of k over m, and therefore r equal to 1 is the first resonance point. Clear? What will happen when, and you can expect that also, because when r is equal to 1, this denominator will be 0, and then you will have maximum amplitude. You can also expect this same thing to happen when r is equal to square root of 5. Will you not? So maybe 2.3 or so, or 2.26 or so, this is the location where the amplitude will reach its peak. That's exactly what is happening, right? So when r is equal to 1 and less than r equal to 1, this is positive and this is positive, so all the responses are all positive. Just look at this. When r is less than 1, the numerator is positive, the denominator, entire denominator is also positive. But when r is greater than 1, what happens? This becomes negative up to this value, square root of 3. These will be positive, but this will be negative. So because of that, you can see that after it crosses the first resonance at 1, the response is actually negative. Okay, and something interesting happens as you keep increasing somewhere here. What happens? Somewhere here, the response of the compressor is 0. And what is that point? At r equal to square root of 3. This is the location 1.7 or so where your response is 0. The compressor does not have any vibratory response, its response is 0. And of course, after this particular point, because this is going to be negative, this is going to be negative, so the total response is positive up to this point where the value of r here is square root of 5, right? So there you get another resonance because of this term, and then you have large amplitude, and suddenly then after this particular case, when r is more than square root of 5, your response is again back to negative value, and that is how the response changes with the force frequency ratio. So the point is, 2 degree of freedom will have these 2 resonances, okay, and the amplitudes will flip from minus to plus as it crosses through these resonances. Let's look at now what happens to the second mass. So we had the compressor here and the raft here, right? And then we are basically trying to figure out what is this x1 and what is this x2 looking like. When you want to find out the raft vibration, okay, it is given by this expression. So here also what is happening, there are 2 resonances, and we expect for a multi-degree of freedom system all the masses will have the same resonance frequency. So the resonance frequency does not apply to individual masses, it applies to the entire system. That is important. So if I plot this variation, it looks like this. So here again you have resonance here and resonance there based on r equal to 1 and r equal to square root of 5, and the frequency at which the compressor response was 0, the response of the raft is minimum here, but it does not flip its sign here, it just continues, and because of the absence of 3 minus r square term in the numerator, it has 2 switchings in the sign of the response, okay. So this is how the response to harmonic excitation to a 2 degree of freedom is looking like. What you should note, that as many number of degrees of freedom that you have, you will have equal number of resonances. So if I add one more degree of freedom, if I include the pitch motion, you would expect multiple resonances occurring here. And this part is very interesting, that at certain frequency value the compressor vibration is going to be 0, okay, and we are going to discuss that part as our next as a part of our subsequent related discussion on this 2 degree of freedom system. Okay, to summarize this lecture, we initially discussed couple of interesting practical examples related to 2 degree of freedom system, and then investigated the response of such systems to external harmonic force. We discussed how the forced vibration amplitude varies as a function of the excitation frequency, and obviously as expected, in contrast to a single degree of freedom system, we could observe 2 resonances. Okay, so recall question here on the basis of what we discussed in today's lecture. So, a simple straightforward question. So, what we learn from this particular example is that in a multi degree of freedom system, even if the system has many natural frequencies based on, of course, the number of degrees of freedom, if the system is subjected to a harmonic force excitation at a particular frequency, the response of the entire system will be at the forcing frequency.